During this session, we will talk about compound interest. We will use the compound interest formulas. We'll talk about computing present value, and we'll understand and compute the effective annual yield. As stated in earlier sections of this chapter, we will be introduced to a set of formulas. Our job is to find the pieces to this formula and use our normal arithmetic procedures to compute the different values associated with the formula. In this case, you see the compound interest formula, where we have the amount is equal to the present value times the quantity 1 plus the interest rate. And as you may recall, the interest rate has to be expressed as a decimal. That quantity raised to the t power, where t is the number of years. Recall that we talked about the baseline for t is 1, meaning 1 year. Here's an example that talks about compound interest using a formula. Again, we're given the pieces to the formula, and we substitute the values into the formula, and we get our result. And recall that when we talk about money, money is presented to us in 2 decimal places. In this equation, $2,000 is deposited into a savings account at a rate of 6%. You want to know how much money you would have after compounding interest for 3 years. Given that we have all the pieces to the puzzle, you see that that value comes out to approximately $2,382.03. And we've talked about rounding to the nearest cents. How much money did we make? In order to find that, we look at the principal that we put in, which was $2,000. At the end of 3 years, we had $2,382.03, and we do our subtraction, find that the interest that we made is $382.03. Continuing with our discussion on compound interest, we see that we have another formula. In this formula, we want to compute the compound interest paid more than once a year, and we introduce a new variable in this equation, and that variable is n, where n represents the number of times the interest is compounded per year. Our example shows that we deposited $7,500 into a savings account at a rate of 6%. And we want to know how much money we will have after 5 years if we compound it monthly. The number of periods during the year that we're compounding is 12, because there are 12 months in a year. We substitute the values into our equation. We come up with $10,116.38. After 5 years, we want to know, well, how much money did we make, or rather how much we have to pay taxes on. In order to do that, we take the $10,116.38 and we subtract our principal from it, and we see that we've made $2,616.38. Another case that we want to look at is continuous compounding. What does that mean? Well, that means that every second, every half second, where the compounding periods become indefinite. If we look at the first equation, we see that we have n, where n is compounding for a number of periods per year. For continuous compounding, we introduce a mathematical term e, where e is the base of the natural logarithm. In other words, e is a number, and it is an irrational number. In looking at an example, we decide to invest $8,000 for 6 years. So in this case, we're comparing 2 accounts. Which one do we want to use? Because we want to get the most out of our investment. The first pays 7% per year, compounded monthly, and the second pays 6.85% compounded continuously. So we want to find out which is better. Given the information that we have, we're going to substitute the values into our formula for compounding interest over periods of time. When we do so, we see that after 6 years, we have $12,160.84. On the other hand, when we're compounding continuously, we substitute our values into the equation. We find that our balance after 6 years is $12,066.66, which indicates that the 7% monthly compounding option is better. That leads us to planning for the future with compound interest. Here you see the equation that we've dealt with before, written in a different fashion in order to solve for the variable P. Most students have problems with this equation simply because you have a fraction in the denominator, and that fraction is multiplied times a number, and then all of that quantity is raised to a power n times t. In order to do this, it is best for you to separate out and compute the parts of the equation separately and then pull your final answers together at the end. Remember, if you're using a calculator or if you're using Excel, do not round off until you get your final answer. Using this equation, we want to know how much money should be deposited into an account that earns 6% compounded monthly so that you will have $20,000 in 5 years. We want to look at the present value formula, and we have the components of that formula, and we substitute those values into our formula. Make sure that you separate out the components of the problem, compute them, and then round at the end. If I round at the end, if I want to know how much I need to invest in 5 years, I'm going to use this equation. I will come up with that. So if I want to have $20,000 in 5 years, I'm going to have to deposit $14,827.45 today so that I can have that money in 5 years. One of the other things we want to do with this equation is look at what we call the effective annual yield or the effective rate. The simple interest rate that produces the same amount of money in an account at the end of 1 year as when the account is subject to compound interest. So in other words, we're comparing simple interest to compound interest. In our example, we deposit $4,000 into an account that pays 8% interest and is compounded monthly. We want to find the future value for 1 year. So we use the future value formula, and we have all the information. We know that our principal is $4,000. Our interest rate presented as a decimal in the formula is 8%. The number of periods is 12 months. And we put in the information and we come out with $4,332. So how do we get the effective annual yield? We look at our basic formula where we have A is equal P times 1 plus RT. We're going to solve for R in that problem. So we know that the future value is $4,332, and then we solve for R as we know how to do by isolating R by itself, and we find out that the effective annual yield based on the simple interest rate is 8.3%. That concludes this section. It's followed by examples that you should work through, and the student pitfalls show that students have a hard time explaining the concept of effective yield The effective yield is the yield based on the simple interest formula. We talked about T being a base of 1. If we're going to express T's in months or days, we have to make sure that we break up 1 into those components. For example, if you're talking about monthly, then T is 1/12. If you talk about quarterly, T is 1/4 because there are 4 quarters. If you talk about weekly, T is 1/52 because there are 52 weeks, and so on. And make sure that you correctly identify N, which is the number of periods of the year. As we talked about several times, make sure that you wait till you finish all your calculations and then round off.